Hello, in this video, let's discuss a little bit about CMOS fabrication. What we are going to do in this video is before we actually go in and look at a sample CMOS process flow, let's look at some of the key process modules that are normally part of any CMOS process flow. Now, these process modules typically induce something known as a layout dependent effect. That is, many steps which are involved in CMOS processing may change the feature that is ultimately made on the wafer, and the change in the feature can be either probabilistic or can be deterministic. So if it is deterministic, an example would be that say a particular corner in a job is rounded, right? If you know exactly how that corner is going to get rounded, then you can correct for that, and this is a very standard process and it's known as optical proximity correction. But there are other variations that occur on the wafer. For example, most of these processes are not uniform over the entire 12-inch wafer. So if I take a very simple example as the length of the transistor is not constant across the entire wafer or across the entire die, even though you might have drawn the standard cell with the same length. So in such cases, it's important to understand what is the variation and then what happens to your product in case that particular variation hits the wafer. So to understand all that, let's first begin by understanding some of the key process modules that are involved in today's CMOS fabrication flow. So the first step I'd like to talk about is photolithography. Lithography essentially means it comes from the process of etching stone. So photolithography is basically a process by which we use optics to transfer a pattern which is initially made on a glass substrate onto a wafer. And we'd like to repeat this pattern over multiple wafers as we create a production line. Now in photolithography, we use a proprietary chemical that is known as a photoresist. And a photoresist basically consists of photoactive compounds whose chemical properties change when exposed to light of a certain wavelength. So here let's assume that I have photoresist coated on some substrate, and what we do is we basically shine light on this photoresist through a mask, and this mask can actually be just a sheet of glass with certain dark areas and certain transparent areas. Hence that means that the photoresist is going to have certain areas which are exposed to light and certain areas which are not exposed to light. And since it has photoactive compounds, the chemical nature of the photoresist changes under these exposure conditions, and you can use that essentially transfer the pattern from the mask onto the wafer. So let's look at a typical use case. Suppose I want to pattern an oxide which is deposited on silicon. So I have a mask that I've created and I'd like to pattern the oxide and create oxide pillars, for example, on the silicon. So how would I go about doing that? First step would involve spinning photoresist on this stack of oxide on silicon, and then we'd send it through the photolithography process, which involves shining light on this photoresist coated wafers through a mask. And the mask typically, as I told you, have dark and light areas. So this pattern which is on the mask gets transferred onto this photoresist, right? And so what you create is basically you create the same pattern in the photoresist. The chemical nature of the photoresist here is different from the chemical nature of the photoresist here. So I can use this property to essentially remove one particular resist with respect to the other. For example, I can remove this red with respect to yellow or remove yellow with respect to red. So in this case, I choose to remove the yellow or the unexposed photoresist through a selective chemistry. So what I've now done is transferred this pattern on the mask to the photoresist. Now the next step would involve using this photoresist as a hard mask and then transferring this pattern of the photoresist onto the oxide. So in this case, what I can do is use a wet etch or a dry etch process to basically etch the oxide in the areas that are exposed. The oxide which is under the photoresist will not be exposed to any chemistries and will continue to stay. And then I can come in with a very simple process which is known as ashing, and that can remove the photoresist from the wafer. So what we have achieved here essentially is that we have transferred the pattern which was on the mask onto the oxide. So I've created an oxide pillar, for example. So what are the salient features of a photolithography process? The primary one is the feature size, right? So typically photolithography is one of the most expensive process modules in a fabrication flow, and this normally limits the cost of fabrication for your product. So minimum feature size is one of the key metrics. Then you also have line and spacing features. You also have to design a process which reduces or which minimizes any 2D effects that are present at corners. We want to define or create a process that gives you straight profiles in the photoresist, right? So once you've etched the photoresist, the profile of the photoresist, you want it to be as faithful as it is to the pattern, because the same profile then gets transferred to the oxide, for example, in this case. The thickness of the photoresist required to transfer the pattern is also important and needs to be optimized. So if you think about the minimum feature size, right? Traditionally, over the years, the patterned gate length was the smallest feature on the wafer. Why was that? Because the gate length of the transistor dictated the drive strength of the transistor. So in digital logic, you wanted your drive strength to be large to keep your delays low. And so you wanted to fabricate transistors with smallest gate length, which was possible at that time. And hence, whatever was the smallest feature size that could be reliably fabricated, that was used in photolithography. And as I mentioned, that determines the cost of manufacturing. And so typically what we see these days is, if you look at a typical CMOS process flow, it can have anywhere between 40 to 50 lithography layers. And what a manufacturer does is, only the critical layers which require the minimum feature size is normally done in the expensive lithography step. All other lithography processes are done in slightly cheaper steps so as to keep the cost of manufacturing down. The wavelength of the laser that is used controls this minimum dimension, and over the years, it initially started off with mercury lamps with wavelengths from 436 nanometers down to 365, followed by KRF lasers and then argon fluoride lasers, both of which got down the laser wavelengths to 193. Now, this laser wavelength determines the minimum feature size. Today, the smallest one can define on the wafer is determined by what is known as EUV, or extreme ultraviolet lithography. Now, as you see here, the cost of the layer increases as you move from these older technologies towards EUV. But EUV is the one that's going to give you the smallest transistor length, hence the best performance for the transistor. And so therefore, when you pick and choose layers, you pick and choose the critical layers in UV, and then for example, for certain metal gate layers, etc., you might go with the 193 or the 248 nanometers. What helped lithography over the last 2 decades has been the process of introducing immersion lithography. That is, by changing the optical stack in the scanner, one was able to draw better performance from these lasers in the scanner. The second technique that we use a lot in processing is deposition. And as the name suggests, it's the technique of putting down material on the wafer, and this material can either be an insulator or a conductor. Typical examples of materials that are used normally would be the gate insulator, would be the gate metal, would be the various metal stacks that one has in the back end. For example, if you look at a 10 nanometer process flow, it may have up to 13 metal stack, right? So every step involves depositing a metal. And then there is a dielectric between these metals. So for those steps also you require some sort of deposition. And so what are the salient features of a deposition process, or what are the things one must care about when one picks a deposition process? So first and foremost is the temperature of deposition, right? Depending on what is the melting point, for example, of the material already on the wafer, any subsequent material you need to ensure that the temperature of deposition is less than the melting point or the denaturing temperature of the material on the wafer. The deposition rate also is an important parameter, especially when we talk about throughput in a fabrication facility. Certain deposition processes have the ability, the template of the substrate is replicated on the deposited material. So that can sometimes be of advantage. Step coverage, that is how this material gets deposited on features which have high aspect ratios. Also, an important consideration would be stoichiometric control, especially if you're depositing compounds or if you're depositing alloys. You want to ensure that during the deposition you have good control of the stoichiometry, and you are also able to tune in the stoichiometry if you want to modulate the properties of the material. Finally, you have to also worry about surface adhesion, because these materials have to, once they're deposited, have to be held on to the substrate. So again, different types of deposition techniques exist. One class of deposition techniques are known as physical vapor deposition. And in such techniques, the material to be deposited is vaporized from a solid and then transferred to a substrate surface and allowed to condense. So an example of this would be, say, thermal evaporation, where you essentially use an e-beam to vaporize the target. You melt the metal and actually sublimate it, and then these atoms are transported in a high vacuum chamber to the substrate, where they condense and form continuous films. The other technique is known as sputtering. And in sputtering, what we do is we use high energy ions which are generated by plasmas to volatilize material from the target and then let it deposit on the substrate. Different kinds of sputterings are available. These include DC, RF, and magnetron. The target material that you want to sputter dictates the type of a technique that you'd use in this case. The other class of deposition techniques come under the umbrella of chemical vapor deposition, in which the material to be deposited is produced using a chemical reaction, and the byproducts are essentially pumped out of the system. Now, the most common technique used is known as low pressure CVD, where we use precursor which deliver the reagents to the process chamber, and then the reaction proceeds and the byproducts, which are usually gaseous, are removed using pumps. So an example of this would be polysilicon deposition. Sometimes plasmas are used to increase the chemical reaction rate, and such a system is known as a plasma enhanced CVD system. Another very interesting technique of doing deposition is known as atomic layer deposition, in which the deposition happens layer by layer, where precursors alternate and hence create the material one layer at a time. So this technique provides excellent step coverage and excellent thickness control. Another special technique of deposition is known as epitaxy, and in epitaxy what happens is that the thin film that is being deposited is actually templated on the substrates. This is used to create films under strain. For example, the silicon germanium in the PMOS is created using epitaxy. Finally, we also have a CVD process which is known as metal organic CVD, and the MOCVD process uses a class of precursors which are organic based, and so these are typically used to deposit 3,5 semiconductors, and the deposition typically occurs at low temperature. Now, etching is the flip of deposition, and it is the process of removing a material on the wafer. So if you looked at our previous example, we used a chemical etch to remove the oxide which was not covered with photoresist. So if you look at the salient features of an etch process, etch rate is one of the primary feature that you'd want. The second one is the selectivity to the, in our initial case of the oxide etch, when we want the oxide to be etched, but we don't want the photoresist to be etched. So you design a process such that it offers selectivity to the other materials present. The third thing is known as the directionality of the etch. So the etch can be designed in such a way that etch rate is higher along a certain specific direction in the material. And finally, we sometimes use temperature at the substrate to modify the etch rate of this species. Now, wet etching is a simplest technique, and basically that means that dipping the wafer or rinsing the wafer with a chemical. Now, wet etches typically tend to be very selective but have very poor directionality. But this is the common technique typically used when we want to cleanse or when we want to do very selective surface prep prior to some sensitive layer deposition. The other etching techniques normally fall under the category of dry etching, where we essentially use plasmas to remove a material from the wafer. Now, the ions that are generated in the plasma are accelerated towards the substrate and eventually vaporize the material that we want to etch. Now, the most common technique here is known as reactive ion etching, where we use an RF source to generate ions and radicals, which are then used to etch the material. Now, because you create radicals, this has a chemical component, so this provides a certain selectivity, and in addition, by using ions, you create directionality, so this provides a high directionality also. The other dry etching technique is known as sputter etching or milling, which essentially is bombarding the substrate with ions. So this has very poor selectivity and directionality, but it is used to get rid of hard to etch materials. Vapor phase etching is an interesting sort of pre-clean process. So here, vapor phase etching occurs when you expose the surface to gas molecules in a chamber, and these gas molecules chemically react with the surface and remove any surface contaminants or surface layers. So this is again a very soft technique, but it's used again in a lot of pre-cleans or surface prep kind of applications. Another key process module in CMOS fabrication is known as chemical mechanical polishing. And this basically involves removing the material from the wafer by essentially abrading the wafer. Now, a chemical component is introduced in this using what is known as a slurry. So this provides some sort of a selectivity in this very aggressive, basically abrading process. An endpointing technique, normally an optical technique, is used to stop the process. And again, this is used especially when we want to remove materials which are harder to etch. And it's also used sometimes when we want to create the surface to be very smooth. And this is very critical, especially when we want to do critical lithography. So why do I need to bother with all this? So the reason I brought up the process modules is that many of these steps like lithography, like etch and CMP, are very dependent on local pattern densities. So many a times design rules that you'll see in a PDK would encompass some of the rules which are dictated by these process flows. And that would mean that it would impact the design of the circuit and the standard cell. Additionally, the electrical parameters may also change depending on the environment in which your transistor is created. And so it is important to understand that, and as I mentioned, at least for the deterministic cases, we can compensate for them prior to tape out.